Like you look at a Mitsubishi Evolution, they've got the full anti-lag system as on the factory car. And all the tables in the ECU are set to 0. But they had to do that to be able to use that in the Group A rally and Group N rally. The turbo system, I think, on the Mitsubishi Evolution 5 onwards, I think is probably the best factory turbo system that's ever been built on any car.
Welcome to the HPA Tuned In podcast. I'm Andre, your host, and in this episode, we're joined by Mark Boxsell from Australia. Mark is one of the OGs of the aftermarket performance industry. Specifically, he was one of the co-inventors of Haltech, obviously now one of the most recognised brands in the aftermarket standalone ECU world. Not only that, though, he moved on to 2 separate areas inside of the automotive industry. Next, he worked on a unique V10 Formula 1 engine design that incorporated rotary valves instead of poppet valves. And if you don't understand what a rotary valve is, don't worry, because we're going to be explaining it as we get into it. Unfortunately, that particular project was nipped in the bud by the FIA changing the rule set before it ever saw time on track, so we'll never know exactly how good that could have been. Lastly, his current business adventure moves into the turbocharger industry, where he's currently the owner of GTpumps, which makes bolt-on stock frame turbochargers for Mitsubishi and Subaru vehicles. This has been a really interesting dive into some of the history of ECUs, the history of Formula 1 engines and engine development, as well, of course, as the stock frame turbo market, how you stand out from your competitors, and we also talk about why plain or dual bearing turbochargers still have a place in this world, and we don't necessarily need ball bearing turbos. Before we jump into our chat, for those who are new to the Tuned In podcast, High Performance Academy is an online training school. We specialize in teaching people how to build performance engines, how to tune EFI, how to construct wiring harnesses. We also cover topics on fabrication, 3D modeling and CAD, race driver education, and data logging, just to name a few. You can find all of our courses at hpacademy.com/courses. All of these courses are delivered in high-definition video modules that you can watch from anywhere in the world, provided you've got an internet connection. This means you can learn from the comfort of your own place, and you can learn at your own pace. All of our courses also come with a 60-day, no questions asked, money-back guarantee. So if you purchase them for any reason at all, decide it wasn't quite what you expected, no problem, let us know. We'll give you a full refund. And for podcast listeners, you can also use the coupon code podcast75. That will get you $75 off the purchase of your very first HPA course. We'll put the coupon code in the show notes to make it nice and easy for you to find. Lastly, if you like free stuff, then I've got a great deal for you. We are constantly partnering with some of the biggest names in the aftermarket performance industry to give away some great prizes. You can always find our latest prize at hpacademy.com/giveaway. It might be an aftermarket ECU or dash. It could be some engine components or engine building tools, or just about anything in between. They are great prizes, and we will ship them free of charge to your door if you're the winner. There's no tricks here, no purchase required to get your name into the draw. All right, enough with our introduction. Let's get into our interview now. All right, welcome to the podcast, Mark. Thanks for joining us. And as always, I want to just get started by finding out a little bit about your background, specifically how you got into the automotive industry.
Oh, thanks, Andre. Thanks for inviting me on. Yeah, well, I actually grew up on the farm near Cootamundra. I actually went to high school in Cootamundra. And I've always had a interest in cars. We had like horses on the farm, but cars were always what I was interested in. Back then, there was no internet, so basically it was all the enthusiast magazines that you'd read. You'd be waiting every month. The latest magazine came out, whether it be motorsport or even just the general car magazines that were really super popular. And then I was involved in the car club at Wagga, just doing normal car club type events, that sort of thing. So yeah, it was just an interest that I followed, I guess, yeah.
Give us a sense, so we haven't really talked about what era this was in, or sort of, what sort of year we're talking about. So what was the technology back then? Are we talking carburetors, fuel injection? Because obviously this leads into where you sort of went with your career.
Yeah, that's right. So this would be around 1984, 1985.
Okay. So that's sort of about the beginning of, early generations of factory EFI systems.
Yeah, that's correct. So, yeah, at that time, well, that was interesting because around 86, Australia went to unleaded fuel, and a lot of the models, the Japanese cars we had on sale in Australia were all carburetted, where the JDM models had already gone to fuel injection. So you're exactly right. That was just at that point where sort of mainstream passenger vehicles started to come out with EFI.
I'm interested in your perspective, sort of living through that at a different era than what I had. I remember I was a young boy when fuel injection sort of became a bit more mainstream, and I remember sort of listening to my old man and a few of his mates sort of dissing EFI at the time, who needs a computer controlling your car? Obviously just that usual resistance to technological change. From your perspective, what did that look like as carburetors sort of phased out and fuel injection became the norm? I mean, when I got involved hands-on with the car scene, EFI was just the way. I've never learned carburetors.
Yeah. Well, because my expertise was in electronics, well, that was wonderful. Everything going to electronic fuel injection.
Right up your alley.
Yes. That made me even more interested.
Yeah, fair. Let's actually roll back a little bit and talk about your sort of education and how you build up that knowledge and skill set with electronics that obviously sort of have served you so well through your career.
Yeah, well, I did a diploma in electronics at college, and I was working in Wagga at that time as a computer technician for NCR Corporation, which is an American computer company. So that was my day-to-day job, was fixing computers and counting machines and all that sort of stuff. So at Wagga, we had quite a big area, like a regional depot there. There was like 4 of us working there and stuff. And we used to come down to Sydney to do training schools when new product would be released and that sort of stuff. So, yeah.
Can you give us a sort of a sense of what a diploma is compared to maybe like an electronics engineering degree?
Yeah, well, it's in between a trade and a degree course, basically.
Okay. At what point did you start sort of looking at putting your skills to use in the automotive industry?
Well, what happened, I really was just working on my own car. And at that stage, I bought a Mazda R100. I bought it off a farm. For all the Mazda collectors there, they'll start crying. I bought it off a farm for $75.
I bet you wish you still owned that.
Yeah, that's right. We picked it up and it was under a tree, I recall, and it had a C's 10A. So I put a 12A engine in there. Actually ended up making my own fuel injection for that. So that's how I got started in actually applying electronics to cars. So, yeah.
Okay, well, let's dive a bit deeper into that. For a start, why did you decide to sort of dive into this project? I mean, that sounds like it's a pretty big project to take on, particularly at that point in time where maybe there wasn't the range of aftermarket fuel injection systems that we have today.
You're growing up on the farm, you have this sense of you basically do everything. We did our own plumbing, we did our own building, our own fabrication.
So you've got that sort of do-it-yourself mentality.
Yeah, there's a sense that, let's just have a go at this, And so I guess that's sort of what I ended up doing. I read every single book I could find at the time. You got to remember, at that time, there was no aftermarket systems at all. And as you were saying, even the OEMs were only really just getting into EFI being commonly available.
How much of a learning curve was this from, you obviously have a thorough understanding of electronics anyway as part of that diploma, so how hard is it for you at this point to kind of apply what you already know in the electronics sort of area to making a fuel injection system?
I guess I learned a lot from the Bosch. Bosch had some excellent publications back then, like publications that would support trade people with block diagrams and all that sort of stuff, general concepts and stuff like that. So, and then, there were some EFI cars, on the market. So I just had a look at the layout and how they'd done stuff, read as much as I could. Like I said, this is before the internet, so you couldn't just Google stuff.
Yeah. On face value, I'd imagine as well, dealing with a 12A and converting that to fuel injection, I would think on face value you've probably picked a difficult engine to start with, given that rotary engines have leading and trailing spark, and ideally you'd like to have a split in the timing between those two. Plus, typically we run staged injection on a rotary engine as well. Were these additional challenges, or did you simplify things down?
I just did fuel only.
Okay. Yeah, that makes sense.
Because that would be like, I wanted to start off with an achievable degree of difficulty.
Yeah, that makes sense. I guess as well that the electronic side of things for an EFI system is really only, I guess, half the challenge. You've also got to actually write software to make it do what you want to do. Is this sort of also in your wheelhouse?
Oh, yeah. Well, this is the interesting thing. The very first box I did was a very simple box just with analog pots and stuff. And we just ran it off the throttle position sensor. So it was extremely primitive. But as you would know, with rotaries, you can be as rich as hell and they still love it. So it was fine.
Just don't go the other way.
Yeah, that's right. And then after I did that, so my version 2 was I actually did a mapped ECU. And it was interesting back in those days. This is like before microcontrollers. So for people that are familiar with electronics, with that sort of stuff, you'd have a microprocessor, and then you'd have a data and address bus, and you'd have these analog to digital converted chips that would measure the sensors and stuff coming in. So what I did was I actually used the analog to digital converted chips, and I used the data buses from those to actually address an EEPROM. So there's a way you can actually, so I actually had fully mapped, I had like 8 RPM ranges and I think 32 load points. So that was actually a fully mapped ignition system with no micro. And I wrote the software to edit the tables on a microbit computer, which is a CPM-based system, which is before DOS.
Wow.
And that was written in BASIC. And microbit was an Australian computer that was in a lot of schools and stuff like that. And I had an EEPROM burner, and yeah, so that's how I got the original, the actually mapped, like a properly mapped fuel map thing. But you have to remember too, like, there was no widebands or anything back then. So you just had to like read the plugs and see how it felt, and things weren't getting too hot. And
I think the current crop of tuners don't realise how lucky we are these days compared to back then. Now you can buy a wideband controller for, I don't know, probably about $200 and that's just going to do the job perfectly. Back when I started tuning, if you wanted a wideband, you were starting to look at sort of lab grade stuff around the sort of $3,000 to $5,000 mark, which for me was just absolutely unachievable. So definitely we're very fortunate with what we've got access to these days. In terms of how it performed, and maybe if you could compare it to how it performed versus a carburetor at the time, which was where you came from, how did it go? Did it do everything you expected?
Yeah, it was awesome. Well, what I used was an IDA Weber manifold, and I built a EFI manifold that bolted to the IDA Weber manifold, and it just had 2 runners that came over the top of the motor with the plenum on top of the motor. I suppose a similar layout to like a Series 4 RX-7, I guess. And we run 2 injectors per cylinder, or per rotor, I should say. And that was mainly because, there was no information on injector sizes. You couldn't just order some bigger injectors, that sort of thing. So, yeah, I just end up doing 2 injectors per rotor. And it was responded fantastically, yeah, and it worked really well.
Coming back to my previous question about the 2 injectors, at this point, were you actually operating them in a staged configuration, or is it just 2 injectors being pulsed simultaneously?
Simultaneously, yeah.
Yeah, okay. Keep it simple.
Yeah. And I built my own electronic ignition system, which was just electronic ignition. It wasn't mapped or anything, because they had points from the factory. And I think it was Electronics Australia kit or something. So I had the electronic ignition running. So I lived at Wagga at that stage. So the closest circuit to us was Winton down in Victoria. So we used to go down and do track days and stuff there, and just normal club, not actually racing, just normal club motorsport, like super sprints, like time attack type events and that sort of thing. Yeah, it was great.
I guess this is also probably in the days before easy access to dynos, so you never really got a chance to tune it on a dyno and see what it was making?
Well, we did actually. That's an interesting question. at Wagga, there's a place called O'Brien's Diesel Engineering, and they have a truck chassis dyno there. So I actually got to run it up on the truck chassis dyno. And as knew I was coming on this podcast, I've got those dyno sheets somewhere, and I looked and looked and looked, and I definitely have them somewhere, but I couldn't find them in time to have something to talk
That's
about. But yes, I actually did run it up on the dyno, and I can't remember what power it made. It was just too long ago. Yeah.
Sure. Yeah, that's understandable. All right. Well, this has obviously set you up pretty well for the next topic we're going to talk about, which is co-inventor of Haltech, which is at this point now one of the sort of the big name brands in the aftermarket ECU space. Back then, obviously, just an idea. How did this sort of come about? And could you also give us a sense of what sort of time this was, what year?
As I look back, and I made a lot of notes and stuff, it was quite remarkable, really, how it all happened. And interestingly enough, it gets back to the magazines that were so popular back then. And one of them was Modern Motor magazine. And you may recall back in those days, I think the magazines still do sometimes, they'll have a project car where they'll buy a car and they'll take it to the suspension people and get a suspension package, and they'll take it to the bodywork people and get some spoilers. They'll take it to the motor trimmers and get some, custom seats done and all that sort of stuff. Well, Modern Motor magazine in 1987 started this Project Falcon. And it was quite a big thing. It was over, I think, 6 issues of the magazine, and it was sponsored by Mobil Oil. And the car in the 1987 Sydney Motor Show was raffled off at the show. So you could actually buy tickets, and there was ads in all Mobil service stations for this, and yeah, quite remarkable. So in one of those issues, actually in the June 1987 issue, one of the things they did was they fitted a Sprintex supercharger to the Falcon 4.1 litre EFI engine. And in that issue, Modern Motor magazine had hired an engineer to run the program, and that guy's name was Edward Visseau. And Ed knew a guy called Stephen Mitchell who was working, I think, Sadgrove and Bauer fuel injection in Hornsby, I think it was. And they needed to somehow change the fueling because they've got the supercharger on there. So in this article was a picture of Steve working in his basement, with all this electronic stuff on his bench. And he was involved in sorting out the electronics on it. So there was 2 things they did. They fitted a bigger airflow meter, because back then was L-Jetronic with the flap airflow meter. I think the Sprintex superchargers were running about 8 PSI boost. And they got, I think it was the flap airflow meter off a M635 BMW, which is obviously bigger. And then Steve rescaled the input, so that would work with the EC4 ECU. And back then, when they were turbocharging, modifying these EFI cars, there was no ECUs and there was no reflashing. There was no. So what you would do, you'd fit a thing called a fueler. So you'd fit 2 additional ejectors, and then you'd have a box which would have a boost sensor in it, and then you'd have a gain and a start pot, and that would give you an adjustable amount of fuel you could add, which was proportional to boost.
Yep. I was involved in a project turbocharging. It was an EK Honda Civic, and I mean, this is in the day where we did have availability of aftermarket ECUs, but obviously everyone has a budget, and this guy was trying to do it on the cheap, and we actually got workable results with just one auxiliary injector, which is essentially run off a pressure switch. I mean, obviously not the tidiest way of doing things, and not a lot of sort of resolution in your fueling when you're just turning an injector on or off, but it actually surprisingly did work. There are a few other tricks to kind of get that all working smoothly, but yeah, that did the job.
Yeah, that's exactly right. So anyway, I saw this article, I got in touch with the magazine, and actually got in touch with Steve and said, Steve, you're doing this stuff. Are you going to, expand the business and do other things? And he said, you come down to Sydney, have a chat. And next minute, we're designing an ECU. Now, he was making the analog fuelers, which is a pot adjustment. But for that car, he actually did a digital fueler. So it was actually one you could actually have an actual map. It was still only a single map. It was still just fuel milliseconds versus boost. It didn't have multiple RPM maps. So he'd done a real-time tunable digital fueler, and he actually used the Commodore Amiga computer as the interface to tune it.
I had one of those.
Yeah, you're right. So that's what he done, and he used bar graphs for the for the table in the digital fueler.
Okay.
And so I had a mappable EFI computer with no microprocessor, and he had a digital fueler, but it was just fueling. It wasn't actually running the whole engine. So it was sort of a match made in heaven, really. Just all their knowledge complemented together, and off we went designing the Haltech. So that's how it happened.
I'm just interested, sort of, at the time, was it more a case of you guys are obviously two smart dudes and really excited about building this EFI system? Had you sort of done much of an analysis of the market? Like, what I'm getting at here is, were you confident there was a market to sell this product to? Because you're sort of at that forefront of the aftermarket ECU sort of industry, aren't you?
Well, I think we did zero market analysis.
Yeah. Okay, that was the sense I got from that, but that's fine. It's all worked out for the best.
Yeah. So it was just a couple of dudes, and we had some other guys in the team as well. Andrew Cowell, who wrote all the original PC software, was written in Turbo Pascal language and stuff. But there's just the most remarkable convergence of technology here, though, Andre. Which you hear these buzzwords like convergent technology, this and that, but that was a point in time that something really remarkable happening. So we had the NGK Uwago had just been released and wasn't widely known. It wasn't widely available, but if you knew the right people, the OEMs were using it to map stuff or whatever. So you could actually buy it. And that was I don't know if you ever saw them, as that blue brick thing that just gave a non-linearized 0 to 5 volt output for your air fuel ratio.
Yep.
Next thing on the list of the convergent technology was the vane eddy current dynamometers. So Australia just led the world in eddy current chassis dynamometers at that time. Next thing was the Motorola HC11 microcontroller. So we were the third user of that in New South Wales in Australia. That's our state in Australia. And that was the very first. Okay, so just to explain, you have a microprocessor, which you might have like in your PC or whatever, and all it can do is computation, right? But with a microcontroller, the microcontroller has on-chip extra functionality. So it has an analog digital converter built on the chip. It has a full timer subsystem built on the chip. And the Motorola HC11 at that time was the first microcontroller that also had electronically erasable memory on there. So this is before flash. It's a type of flash. It's not like actually the technology is slightly different to flash. It's effectively, if you want to think of it just for people listening, it's just basically flash memory. So it was the first microcontroller with on-chip flash.
So in other words, you were getting away from these removable EEPROMs that you had to burn.
Yes. And so you literally had EFI computer in one chip. Okay, you had to put a few drivers and things to run the injectors and stuff, but basically that. And then the other thing of the four things was laptop computers. Laptop computers had only just come out there. It's quite remarkable when you think of all that, just all happening at the same time.
Yeah, it is one of those sort of unique points in time where if you tried to do that 3-4 years earlier, it just wouldn't have happened. Right place at the right time.
And I remember when we got our first shipment of HC11s, on the invoice from the supplier, it had a notice on the bottom from the US State Department saying that this chip cannot be exported to the following countries, which was Russia, Iran, North Korea, without specific permission.
Wow.
This thing's pretty high tech if they're worried about where it goes in the world, so.
I'm interested, just a little off topic, but I'm definitely not an electronics engineer, so I'm very much on the edge of my knowledge. But that HC11, like, how does that stack up against what we've got access to for our current ECUs? It
was remarkably powerful. Okay, it was an 8-bit micro, but it did have 16-bit divide and multiply instructions, which was pretty advanced at the time. With that chip, though, we had the on-chip. I talked about how good having the on-chip memory, but the on-chip memory, we had 2K of the flash style memory. Only had 256 bytes of RAM. So not 2K of RAM, 256 bytes. So we had to have, and so you had to have the code and the maps in the 2K of memory.
So that sounds like a challenge.
And it was just a mega challenge. And so we actually wrote, everything is written in assembler, which is pretty much the most basic way you can program, because like using a C compiler would have taken up too much space.
I'm guessing at the same time, though, we were also dealing with simpler engines. We weren't dealing with continuously variable cam control. There was no drive-by-wire throttle bodies. So I guess the demands on that controller would have been much less than what we need today.
Well, yeah, I would say so. However, I mean, that HC11 processor was also used in the GMP4 ECU, which is what was in all the Commodore, all the from VN Commodore on in Australia, and earlier versions that had been used in America. So obviously the big OEMs have access to the big electronics companies. They get first access to some of this new stuff. In fact, when you look into some of it, a lot of things were specifically developed for the big companies to do this sort of stuff.
Yeah, naturally. Yeah, I guess the OE numbers compared to even the biggest aftermarket ECU companies, they're just not even on the same level, are they?
Oh, no, that's exactly right. But I mean, this was a general purpose microcontroller. So the class of electronics that all these ECUs goes in is a class called embedded control. So embedded control is a computer that basically boots up and just runs a run program. So embedded controllers are running all kinds of stuff like, lifts in buildings and running fan motors and air conditioners or whatever. So their only mission is once they switch on, they just run this one program their entire life, basically. So the HC11 had a lot more uses apart from just automotive as well. So, yeah. But to give you some idea, like the problem wasn't the processing power, it was just the amount of memory you had. So as I recall, at 6,000 RPM, one engine revolution takes 10 milliseconds. We were running the whole code for looking up the tables, doing the air temperature correction, barometric correction, whatever. That was only taking like 1.5 milliseconds. So we had plenty of headroom as far as processing power and stuff. Yeah.
Right. Well, once you had this ECU up and running and you tested it and you're sort of happy that it did everything it should do, at this point, because we don't have the number of ECUs available, aftermarket standalone ECUs available, I'm guessing there's also a bit of a case of kind of training the market that this product exists, what it can do, why people need it.
Well, this was the problem, Andre. Well, wouldn't say a problem. It was the challenge is we had to teach people how to map engines. Wouldn't it be good if there was some dude with a website we could send people to learn how to tune engines? Do you know anyone who that might be?
Well, it's funny you should say that, because the whole reason that we exist today is we created what I wanted and would have paid money for when I was trying to teach myself how to tune. I mean, you can absolutely get there. I'm proof that you can teach yourself how to tune without the resources we offer. But I tell you what, having the resources we offer would have fast-tracked my learning curve dramatically.
Yeah, absolutely dramatic. Well, see, and so, yeah, we had to teach people how to tune. So that, and our first ECUs were fuel only. So that we had the F2 and F3, they were fuel only. Then we did a standalone ignition box called the IG4, which was a separate box which just did the ignition. So if you did a car, you'd run the IG4, the ignition, and the F3 or F2 for the fuel. We had cars run at Bathurst like that in the VAD Supercar Championship, in the Group A cars and stuff. And then it wasn't until the E6 came out where we had fuel and ignition in the one thing. And then in the E6, we had external memory for the program. So that got rid of all the problems with not having enough space for extra code and doing extra things and that sort of stuff. But the F2 and the F3, they had separate barometric correction, air temperature correction built in. They're actually pretty sophisticated, like for their day and what they did. They programmed a warm-up curve, like you had a table for warm-up and stuff.
Yeah, I think that was probably my introduction to Haltech, and one of the real obvious things that Haltech used, which stayed for a long time, was the sort of 2D bar graphs for tuning fuel and ignition. And I'm interested to dive into that, because for me, I didn't cut my teeth on the Haltech brand. Because we're based in New Zealand, I started out with Link, a New Zealand-made company. And Link, along with probably the majority of the competitors, with the exception, I think, of Microtech, used a conventional three-dimensional table of RPM versus load for both ignition timing and your fueling. So I was used to that, and that's just how my head worked as a tuner. And I did find it quite difficult to get my head into the game of tuning using these bar graphs, particularly when you couldn't see all of the bar graphs together, because obviously they're two-dimensional. So I'm just, what was it that made that the user interface that you adopted?
Well, it was still a 3D table, a full 3D table with interpolation, but it was never displayed that way.
Yeah, correct, yeah. Sorry, why I mention that is, for me, I find that is really easy. This is a trap that is easy to fall into if you're viewing a fuel table, for example, just as numeric values. Maybe that's volumetric efficiency, maybe it's injection time in milliseconds or whatever. It's difficult to spot an outlier where maybe you've made a mistake or the decimal point's in the wrong spot or something like that. And that as a number can be really easy to not see. And when you look at that fuel table then in a graphical format, you can instantly spot an outlier, be it one cell that's massively too high or massively too low, and that makes it easy to fix. And that's the point I'm sort of getting to with the bar graphs. While yes, it's still a three-dimensional table, you can't view that all together. So I found I could get some sort of holes in the fuel table that weren't as obvious as they would be if I was viewing it three-dimensionally.
No, that's fine. Well, this is interesting because this comes back to we had to teach people how to tune or how to map cars. So we had to make it as easy as possible. And so the bar graph was used because we had the arrow that used to write on top of the bar graph to show you what. So it was absolutely so ridiculously obvious that that's the load point you were at. And with the chassis dynos back then, and I'm not including the DynoJet inertia roller dynos in this, but there was none of this ramp testing stuff. You would just go to a set RPM, and I mean, the dynos they didn't have the software to do actually the ramp testing. So basically, you'd just go to 3,000 RPM.
And then work your way through that particular slice of the pie.
That's right. You can just be 3,000 RPM, you have your foot on the throttle, and you can literally just move your foot, and you can just move the load points across the bars and just see exactly where you are. And you do 3,000 revs. Okay, that's good. You go up to 4,000. Obviously, 3,000, will influence the one above, but basically that's the methodology you'd use. And so that's why it was sort of designed that way. And it was even designed so when you were sitting in the car and the laptop's on the passenger seat facing you, you could use it with one hand because you might have your other hand on the dyno controller. And so that's why to come from the back, to come back from map or space bar to come back out, because that was super easy to reach and press. And, page up, page down, the up and down arrows. So it was all designed to make it easier to tune on the dyno. And that was the whole concept about it.
Yeah, I mean, when you put it like that, that makes sense. I don't think I ever used a dyno that couldn't do, sort of a ramp run. So that's kind of just my experience, and I guess that differs from that time.
Yes, that's right, because the whole ramp test stuff didn't exist back then. On a Superflow engine dyno, they had like a step test, and you could step 500. You could say how many seconds you wanted to stay there or whatever, but it's still stepping. So yeah.
I'm just sort of thinking while you're talking about that, it must have been a bit more tricky, a bit more challenging to tune anything that was actually making some serious power, because you'd have to hold it at high RPM under high load for a much more extended period of time than you would with doing a ramp run, right?
Oh yeah, exactly right. So
what I guess were the biggest challenges you faced building this first Haltec ECU or the first Haltec ECUs?
I think because we had done enough background, it all came together like remarkably well, because it was in November 87 we actually filed the patent for the system. So yeah, I guess we just had some good people, and we had a few noise issues, RFI and that sort of stuff. But because it was a fuel-only system, it was quite remarkable. If you want to do a demo with someone, you could sort of, and they had, they fitted the EFI manifold. You could literally turn up, you could drape the whole harness across the engine bay or whatever, hook up to the negative side of the coil, maybe and set the air temperature sensor, and then you can literally start the car and get it going almost immediately. So it was a good way to sort of introduce everyone to that without having to worry about all the ignition side of stuff,
Yeah, I guess now, with the technology we've got available, is just the standard. We accept it, we understand it. But back then, the OEs weren't doing what they do now. So, you're kind of in a situation where you don't know what you don't know.
Yes, and I think getting back to your example with your Honda and that injector, it's remarkable how good you can get things with just a basic, well-designed system, so...
Yeah, I think sometimes these days we sort of tend to unnecessarily overcomplicate things. And I reckon the issue here is the more levers an ECU provides to the tuner to pull, for the average tuner who's maybe relatively new to things, that allows you so much power and control that you can get yourself so far out of the ballpark that you can't actually find your way back. So sometimes I think where I'm going with this is less is more, and just get back to the basics: fuel, ignition. That's all we really need.
Absolutely, yes.
There's sort of layers of sophistication, and then we start getting small iterative improvements in drivability, performance, fuel economy, etc. Yes, I mean, those are all important, but you can do a pretty good job with just the basics.
We just absolutely do a fantastic job with just the basics. In actual fact, the F3 computer, which is just a fuel-only box, was an interesting project. This is another remarkable thing in a way. So Lada Australia, the Russian car Lada.
Yeah.
Lada Australia did a project by fuel injecting a Lada Niva four-wheel drive. And they cast the inlet manifolds in Australia, everything was just a magnificent project. And that used one of our F3 computers on there. It was full Australian design rule compliant. I actually went to the emissions testing at EPA and everything. And that's the first time, and probably the only time, certainly in Australia, the only time an Australian developed ECU has been used on a car in Australia. So that was pretty cool thinking back to that.
Yeah, it's a great claim to fame. At this point, you just mentioned you filed a patent. You do have other competitors in the aftermarket ECU standalone realm at that point? What I'm getting at is, I mean, I'm struggling with my history, but I didn't think that Haltech was the very first.
Well, let's jump back to how do we go about marketing this thing? So Ed Vusso, the guy that was in charge of the Modern Motor Supercharged Falcon project, he organised a marketing trip to America. So in 1988, myself and Ed went to America and visited a lot of the major tuning places, and we demoed the stuff. We went to Art Whipple's place in Fresno, California. And that was quite interesting, Andre, because he was more interested in the Uago than the EFI computer because he'd never seen one before. And we did demos at just different places. And at one place, and like I said, you could just walk in, something was already all plumbed up. You could walk in, hook up the thing and fire a car up, So we went to this one place, and I can't remember where it was now. We visited about 10 different places. It was a big trip. And I said, okay, and we're on the rollers. We're just running up. We're just doing to part load, just not really putting much power, just revving it up, just rolling the rollers a bit, and just sort of getting some sort of ballpark tune so we could actually put some load on. And getting back to my point about eddy current dynos. So I said, okay, so what we need to do is let's just, like the fuels are right, just download. What we need to do is just hold it at 3,000 revs, and I'll show you how you can go across the thing, across the load maps with the bar graphs and stuff. And he looks over to me, he says, we can't do that. And I said, what do you mean we can't do this? Oh, no, this is an inertia roller dyno. And I thought, what sort of you know what I mean? I've upset all the dynojet operators in the USA now. So
I've had very similar experience. I've tuned using a dynojet inertia dyno a number of times, and again, I'll probably get a few dynojet owners offside with me, but I mean, personally, I feel only viable use they have is for tuning drag cars.
Yeah, I think so.
You definitely can't do a great job of part throttle or drivability. But just coming to your point there, from the start of my career, as far as I was concerned, the engine dyno was just the holy grail. This was going to be the perfect thing for tuning an engine on. And I'd only ever had access to a Dynapack hub dyno, which, don't get me wrong, great piece of kit. And I got commissioned to do a calibration on a Marathon Jet Sprint boat motor, which was a supercharged Buick V6, and this was on an engine dyno, so this was going to be the best experience of my life. And I turn up to this tuning shop, and the engine's on the engine dyno, everything's set up and ready, and we get it running, and I sort of asked the dyno operator, I want to go to 2,500 RPM, and I was just going to start, filling in the fuel and ignition. and it's all manual controlled, so he's sort of opening and closing a tap and, working the throttle, and all he did was drew a big circle around the cell that I wanted to go to. And I quickly realized that this dyno was maybe not quite what I had expected. Now, granted, these days, obviously, there's engine dynos with high quality digital control, and that's no longer an issue, but it was a very rude wake up, the technology that kind of was the norm at the time. Maybe that would have worked fine for carbureted engines, but when you've got a massive three-dimensional table of fuel and ignition numbers, that just wasn't quite going to cut it for us.
Yes, yeah, that's right. We did a lot of tuning on the Group A V8 supercar engines that raced at Bathurst. Well, they weren't called V8 supercars back then, but the Group A Commodores and stuff. And we did tests on the Superflow 901 dynos and stuff, and they were fine. You could hold a load and do the mapping on those, so they were great for that sort of thing. And they were around back then when we started Haltech and that, so yeah.
Okay. So what was sort of the trigger for the growth of Haltech at that time? And how long did it sort of take for it to really get some market exposure and get a bit of uptake from customers?
We had a big stand at the SEMA show in 1989, and it just exploded basically. And you were saying about competitors and stuff. When we went to America, can you imagine turning up at America to display a product and there's no competition?
Is that literally what it was?
That's literally what it was. The only thing that was around back then was, and I don't know if anyone even remembers this, there was a thing called the air sensors EFI system, and that was particularly tailored to like small block Chevs and stuff. And so they had like a Holley throttle body arrangement with a hot flow airflow meter, and they had like a screwdriver adjustment. And that was literally the only thing on the market in the USA. Probably about a year before us, but we beat them to America effectively.
Right. The next sort of thing that I've got in mind over this is when you're in a market with no competitors, I think there's a blessing and a curse with that. Obviously, customers don't have a lot of options if they want your product. But you don't also get to see how other competitors are dealing with the challenges of controlling fuel injection, what features, functionality, software, how's their user interface look. So how do you, from your perspective, is that a blessing or a curse that you kind of have to forge your own path and figure it all out, as opposed to maybe, I wouldn't say necessarily copying others, but seeing the direction they've gone and going in a similar route?
Well, I think we were just so far ahead of everybody that wasn't even in our minds, We had a path to go on and we just went for it. Now, interestingly, one of those places we visited on that marketing trip in 1988, we went to Texas and we did some demos of the equipment, and to a guy with an electronics company called iTech Systems. A friend of his was Corky Bell.
Oh yeah, I've got Corky Bell's turbocharging book.
Well, I've had dinner at his house.
Oh, wow.
So here's a dude who grew up on a farm, and we were only young then, obviously. Well, we wouldn't class where we were as outback, but out in country New South Wales. We weren't that far out west. And 2 years later, here I am having dinner at Corky Bell's house in Texas. So the guy at the electronics place had asked Corky to come along and look at our demos and stuff and make sure it all looked above board or whatever. And so at that point, iTech Systems signed a license agreement with us and started making the Haltechs in America under license to us.
Okay. I guess that American market is always going to be the key to success because of its sheer size, right?
That's right. We just realised that if we get this in America, that this is where it needs to go. Yeah.
One sort of question I've always had in my mind from when I was running my tuning shop: why are there so many aftermarket standalone ECU companies that were founded in Australia? And I sort of did a quick sum up, and I may have missed a couple, but we've got, that I am aware of, Autronic, Motec, Adaptronic, we've got Wolf, Microtech, EMS, Mtron, and Haltech. That's a lot for what is, in terms of the US size, Australia is still a relatively small country.
Oh yeah, that's right. Australia was literally number one in the world for that product range. And we've spoken to, I guess we all know one another more or less. I actually run into Richard Bendell, who started Motec only this year. I hadn't spoken to him for years, and it was great catching up to him. And we'd spoken online, but actually seeing him, I hadn't seen him for like over 20 years. It was good to say hello and shake his hand or whatever. And we actually spoke about that, and we're not sure why. We couldn't really come up with a reason why that was, apart from, I guess you being in New Zealand to understand this, well, we're sort of halfway around the world from everything. So maybe there was a thing, well, there's nothing on the market, we just have to do it ourselves. Maybe that was part of it.
Yeah, I think from my perspective, Australia and New Zealand have, this is no disrespect to North America, but I think maybe because traditionally, it's changing, I think, but traditionally we had less available resources out of America. Back in the early days, freight was just prohibitively expensive. So, I mean, rather than sort of bolt-on upgrades, I think in New Zealand and Australia, a lot of people focused on more making upgrades from scratch themselves. Turbo kits, for example, you wouldn't buy a turbo kit, you'd fabricate an exhaust manifold, buy a turbocharger, and you're away to the races. So I guess the same mentality applies to the fuel injection industry.
I think so, and I think the workshops in Australia and New Zealand are very skilled, like they'll weld things up, make things, whatever. I remember when we did some marketing trip to the UK, a lot of the tuning places there, it was all about kits. You would buy a kit from someone else and fit it to the car. You wouldn't design something, make the piping and weld up a manifold, figure stuff out. It was all about kits. That was their whole mode over there. So it was a whole different way of approaching things, yeah.
I think that mentality of the upgrade kit also at that time was probably mainstream in the US too. And again, yeah, we were just sort of making things to suit as required. I mean, looking at it from a commercial viability standpoint, that's not a great way of running a business if you're modifying cars for a living, making everything as a one-off from scratch, but sometimes needs must. All right, so if we sort of fast forward a bit, how long were you involved with Haltech before you moved on, and sort of what was the reason for that?
Well, I ended up leaving in 1993, and so I was actually the last one of the original design team to leave. Steve, he went to America with ITAC Systems to do the technology transfer to make them in America. They hadn't been made in America for years. I can't remember when that arrangement finished. I don't have a date for that, but it would have been in the 90s somewhere.
And these days, Haltech, at least to the best of my knowledge, are quite unique in that they're the only ECU company that I'm aware of that are making all of their boards in-house.
Yeah, that's right. They've got their own surface mount pick and place machine, everything. Yeah, that's exactly right. So they're the only people who do that. Like Motec contract all their assembly out and that sort of stuff. So
yeah, I've always sort of thought there must be a sort of a pros and cons with that, just like anything, but I guess for rapid prototyping, particularly if Haltech these days are developing a new ECU, must be much faster, not relying on outsourcing the actual construction of the boards.
Yeah, no, absolutely. And just jumping back a bit, I know you probably want to move on a touch, but something important about the Haltech stuff was we weren't ex-anybody. So one of the only ECUs, like you say, for example, the Zytec system. So the Zytec system out of UK, we were a couple of years behind them, but both those guys were ex-Lucas. They came from Lucas,
So they basically already had some runs on the board. They had experience in that market, but you were coming to it from nothing.
You were come from nothing, and my own personal interest was also ignited by, I should have said this to you earlier, but reading the magazines about Don Devendorf and the electromotive Nissan team racing in America. So Don Devendorf, he was an engineer that worked at Hughes Aircraft Corporation working on satellites and stuff. And he'd actually made his own fully programmable fuel injection computer. And I remember reading all the articles about that, and I thought, I'm going to have a go at doing this.
Inspirational.
Yeah, no, it was inspirational. And then people say, I had people say to me too, like, oh yeah, Haltech used those bar graph things, And well, the reason no one else used them is because they were in the patent.
Ah, so they couldn't.
So no one else were allowed to use the bar graphs. And you might notice how Link has that, and I'm trying not to upset Link, good guys Link, that annoying store the maps to the ECU before you switch it off thing.
Yeah.
So that was to get around the real-time programming that was in the Haltech patent.
Oh, so they weren't allowed to do that either.
And then the Motec, you might have noticed all the Motecs on their cables, they had that box. And you think, well, why on earth was that there?
The number of times I wondered that.
Well, that was because of our Haltech patent.
Yeah, that made absolutely no sense to me. It's like, why do we need this box?
Yes.
Just connect the damn cable to the computer.
Yeah. It wasn't a direct interface to the ECU.
So there's always reasons behind these things that we as tuners sort of wonder about.
Yeah, that's exactly right.
I just wonder if you can give us a perspective now on sort of what you sort of think of where Haltech have got to. Obviously, their current range of ECUs are sort of not in almost any way comparable to where you started, but technology's marched on. But yeah, you're sort of proud of that sort of what you started is still going and has now become such a strong player.
Oh, I think it's magnificent. Yeah. When you see the stuff they have, the hardware, and you think, it's just a bunch of young guys started that company. Like started that, invented that product. Yeah, it just gives me a warm feeling inside when I see those guys, doing their stuff, and good, all the best. Good luck to them,
Yeah, I can imagine you'd be pretty proud. I just want to take a moment out of our chat with Mark to talk about a package of courses that I think you're really going to enjoy, and that is our tuning starter package. Normally valued at $417 US, you can use the coupon code GTpumps100, and that will take $100 off that purchase, bring it down to just $317 US. This package of courses is designed to get you from zero previous knowledge with tuning up to a point where you are confident and competent to start tuning your very first car. The course starts with our EFI Tuning Fundamentals course, which teaches you the core tuning principles and techniques that you'll need to understand in order to be able to tune any engine on any ECU platform. You'll learn how the engine operates and how the ECU functions. You'll learn what we're trying to do when we're optimizing both fuel and ignition timing. Next, we include our Understanding Air-Fuel Ratio course, which I think is probably one of the most misunderstood topics in the world of EFI tuning. We'll teach you how the air-fuel ratio affects engine operation. We'll give you some safe starting air-fuel ratio targets for your engine so you don't risk damaging it while you're starting to get up and running tuning it. And then most importantly, we'll teach you how to optimize and find the correct air-fuel ratio for your engine and your application. Now we move into our practical courses, and we've got our practical standalone tuning course, perfect for those of you who want to learn how to tune aftermarket standalone ECUs, much like the Haltec ECU we've been talking to Mark about today. Also, we've got our practical reflash tuning course, which is going to be perfect for those of you who want to learn how to reflash or recalibrate the factory-fitted ECU that came equipped in your car. Both of these courses are generic, so don't worry, it doesn't matter what type of ECU you want to tune or what type of engine you're tuning, these courses will be perfect. Both courses include a step-by-step process that you can apply to your tuning, and this way it breaks it down from what on face value seems like a really big, scary job into simple, bite-sized steps. Each of these steps can be relatively quickly and easily completed, and in no time you've got to the end, you've got a completely tuned engine delivering great power, torque, and most importantly, great reliability. Both of these courses also include a library of worked examples, which is an informal walkthrough of our step-by-step process where you can watch the process being applied from start to finish on a real tuning job. Here, we vary both the type of car or engine we're tuning as well as the software that we're using to tune. This package also comes with 24 months of gold membership, which gives you access to our private members-only webinars, and these are held every week. If you can't watch them live, you can rewatch them in our webinar archive, where we've got over 350 hours of existing content. This is an absolute goldmine and one of the fastest ways to expand your knowledge on a huge range of performance automotive topics. Our gold members also get access to our private members-only forum, which is the best place to get reliable answers to your particular questions. Total value of that package is $1,100 US, normally $417. Again, remember you can use that coupon code GTpumps100. That'll get you $100 off. You can still use our payment plan to break that payment down into as many as 8 individual weekly payments, making it as cost-effective and affordable as we can. You are also still protected with our 60-day, no questions asked money-back guarantee, so there is zero risk giving these courses a test drive. The coupon code will be in the show notes to make it easy for you to find. Let's get back to our chat with Mark now. We could probably spend another hour on this, but we've got a lot to get to, so I'm gonna move forward. I'm just gonna quickly mention this next one because I just don't think we're gonna have time to do it too much justice. But post Haltech, I know you're also involved in another Australian company, M&W Ignitions. I just want to really briefly talk about this because M&W has sort of become the gold standard if you're building a drag car that's going to be high output capacitive discharge ignition systems that are going to be able to light off a spark when you're running 50, 60, 120 psi of boost at 10,000 RPM. So can you quickly give us a sort of a comparison of the difference between capacitive discharge ignition and a conventional inductive ignition system? And then following that, why is CDI the pick for high output engines?
Oh, yeah. Okay. So, well, just to lead into M&W quickly, M&W just stands for Mark and Wayne Ignitions. And that's my business partner, Wayne Glasser. He's like ex-Qantas aircraft engineer dude, really smart guy. And so when I left Haltech, I thought by that stage, the other competitors on the market. So I thought, well, I don't really want to design another ECU or something and compete with all these people. Maybe there's something else I could design that everyone would use, they would all use. And so that's how we ended up doing all the ignition stuff. So we were supplying ignition modules. We had the inductive ignition modules in the early days. We were supplying everybody to start with. And then from then on, we developed the CDI system. And this is before all this smart coils and that sort of stuff. So the CDI especially had advantage with the V8 when they're only a distributor because the inductive ignition didn't have time to recharge the coil at the higher RPM and stuff. So it was obvious use of CDI ignition. So the advantage with the CDI, the capacitive discharge ignition, is basically with inductive ignition, you have a magnetic core, basically. You pass a current through it, which establishes a magnetic field. You switch off the power to the coil. Magnetic field collapses, and in collapsing, it transfers that energy out through the spark plug. So capacitive discharge ignition is completely different to that. With the capacitive discharge ignition, the energy is stored in the capacitor inside the ignition box, and at the time of the ignition point, that capacitor discharges through the coil. So the coil only becomes just a transformer. It's not an energy storage device. And the main difference between CDI and inductive ignition is actually the rise time. So with the CDI, you get a massive current. And you have, when I say rise time, we're talking about the voltage differential across the spark plug gap. So the quicker you can get that happening with the more energy, the more you'll ionize the particles in there and you'll get that conduction for a spark. And if you've got a highly turbulent combustion chamber, there's lots of, it's blowing a gale in there, basically, you want to be able to light that spark reliably every time.
So compared to inductive, we can get problems reliably lighting off the spark when we've got very, very high cylinder pressures, but the additional energy essentially supplied by capacitive discharge means that that's no longer an issue.
That's right. And so, you might be discharging, the peak current through the coil might reach like 150 amps. And in an inductive system, you got like 9 amps or 10 amps maybe that you're collapsing. So that's not a direct analogy, but it just gives you some idea of the difference in the energy. Okay, the CDI spark can be a shorter duration.
Now that shorter duration of the capacitive discharge spark, that can in itself be problematic. And I think it's sort of more, from my own experience, I've found that CDI can be problematic around light throttle cruise, but still work really well at sort of wide open throttle, high load. Is that correct? Yeah.
Yeah, no, that's right. Although typically you wouldn't really see that, I think, in most performance applications. Depends what coils. When we used to use the old Mercury coils, they had a super short spark duration, and that wasn't ideal. And we have our own coils now would actually give a longer spark duration. So you're right. There are two aspects. There's the initial fire, and then how long the spark is there for. But you have to remember, in a combustion chamber, once the combustion is ignited, it's burning away from the spark plug. The flame front's burning away from the spark plug across the combustion chamber. So once the thing's lit up, it should be okay.
Job's done. Yeah. I'm interested in your take before we move on. You mentioned this is when you were developing these, there were no smart coils. We didn't have at least to the best of my knowledge, there weren't a great selection of good inductive coils around that were going to suit at least the drag applications that I was involved in. So this was a no-brainer. These days, I think things have moved on. We've got some really good inductive coil options, the likes of the IGN1A, the GTR R35 coils that have been well proven in high boost methanol engines. Is the case study for CDI maybe not as clear cut these days?
I don't agree with that. I mean, if you go to T1 in America, who are a big R35 tuner over there.
Yeah, now we've had Tony Palo on the podcast. We know his work well.
Yeah, and they're also one of our MW distributors. One of the things they have on the online store is a kit to pull off the R35 coils.
Okay. I guess when you're pushing these engines hard enough, at some point, probably no inductive system's going to be able to cope, correct?
Well, look at, the Michael Koval's Evo 6 that you've seen videos about and stuff. He's running 83 pounds boost. Well, he's running MW CDI on that. And if we just say jump to Bonneville, Speed Demon 715, which is the fastest piston engine wheel-driven car in the world, at 481 mile an hour at Bonneville in 2020, is running MW CDI on that.
Yeah, okay. It's a pretty good CV. Plus, if we were talking off camera before we started recording, and at the time, the Supercar series, you were basically the control ignition system.
Yeah, well, so we supplied Maytech with the CDI, which was the FIA control system for that whole series for over 10 years.
Yeah. And for those who haven't heard of the Supercars series, maybe from North America, I mean, in the Southern Hemisphere, that's the sort of the highest level, essentially, of tin top race cars.
It'd be like supplying Winston Cup, NASCAR series for 10 years, and with every car running that equipment.
Yeah. Okay, I think we'll have to park that there because I've got a bunch more that I want to get into, and this one's pretty exciting for me. You're also involved in some engine development work, sort of in the earlier days of Formula One, and it's not too often we get a chance to talk to someone who's sort of been involved at any level in Formula One. The interesting part for me here is the engine that you're working on, which is the Bishop rotary valve engine, and I've done a bit of research. We're going to link to an article in the show notes that people can read if they want to learn more. But this was basically destined to become a V10 Formula One engine with rotary valves as opposed to poppet valves. And again, we don't have the benefit of pictures here in our podcast, but if people do want to see what we're talking about, that article will explain that. Let's roll back to the start of this. How did you sort of move from working in electronics to working in engine development?
Okay, so when I was at Haltech, so the rotary valve was done by a company called Bishop Steering. It was actually a sub-company of Bishop Steering called Bishop Innovation. And they had a rotary valve program. I'm not entirely sure how that came about, so I won't speculate there. But Tony Wallace was he was in charge of that. He's a very interesting guy in his own right. He's an ex-Repco Brabham guy, and he was running the rotary valve program at Bishop. And they were using an XT500 Honda single-cylinder engine from a trail bike, and they put a rotary valve head on, and they were just using the carburetor, and they wanted to convert it to fuel injection. So we'd supply them an F3 fuel computer that they'd used for that. And then they kept working on that. I didn't have anything more to do with them. They kept working on it for many years. And after I left Haltech, I went to a place called Kelray Australia, which was like automotive parts supplier, basically supplying. We did OEM stuff as well, whatever. And sitting there one day, I got a phone call from Tony Wallace, and he said, we're upping the rotary valve program. Do you want to come and have an interview? Because we'd like to have you on board. And so I go to the interview and I signed the non-disclosure agreement. And after I signed that, he tells me that the developments of Formula One. I just said, I'm in. It was committed already.
Yeah, I can understand that.
And so my job there, because of my background in electronics, my job was basically to do all the instrumentation in the dyno. And okay, so just to put people in how all this works. So if you're doing a V10 development, obviously you're making changes to the engine like you would in a normal type engine development. But you think, let's change the port angle by 3 degrees, So you can't just get like your old Chevy head and get in there with the die grinder and stuff, because all this F1 stuff is all super thin wall casting or whatever. So they actually have to cast a whole new head, and then they've got to do a left and a right hand head, and then they've got to build the engine. So you can just imagine how just astronomically expensive that is.
These developments do, though, start with a single cylinder that then is scaled up into a V8 or a V10 or a V12, right?
Yeah, that's right. And even Cosworth had a single cylinder program there. I saw a video on that the other day. So I think everyone was doing that. And then you had a single cylinder, and you could just have a billet head. So you could just do as many iterations as you wanted to. I mean, and you could do all kinds of useful things, even like as mundane thing like piston ring wear tests and all kinds of stuff, So yeah, if we're going to do the rotary valve development, we're going to do it on the single cylinder engine. So my job was to look after the dyno. And also, I built in my own time as a bit of a design exercise. I actually built my own ECU, which actually got used in that project. The single cylinder F1 was running my ECU. It was also running M&W ignition as well on it. With the rotary valve stuff, there was a lot of first principle stuff, because with pop-up valves, there's just a vast library of SAE papers, but when you go to rotary valves, there's very little of substance there. So
yeah, I've heard of rotary valves. I've not got a lot of knowledge on them, but at this point, had the rotary valve sort of concept been tried by other competitors?
Yes, it had been tried by various people. There's the Coates rotary valve. You often see articles on that or whatever. But one of the major difference with the Bishop rotary valve, it ran in the head with clearance. Where a lot of these other valves, you see, they'd have a sandwich head, and the thing would have to seal in that rubbing on the aluminium cylinder head surface and that sort of stuff. Where the Bishop rotary valve actually ran with clearance. So there was a clearance between the valve and the cylinder head. And we actually had a seal arrangement similar to what you have on a rotary. So, a rotary, you have your apex seals and you have your side seals. So we use a similar type of sealing mechanism, although the difference between the rotary and the rotary valve implementation of the seals was the seals were in the head. So they were stationary. They weren't spinning in the valve or whatever, and they just rubbed on the valve as it went around, and that's where we got the sealing from. And so the main thing with the rotary valve was volumetric efficiency. I mean, that was the promise of that whole thing. And, also, if you look at it from a Formula One point of view, you don't have any issues, like you've literally got no valve springs and all that sort of stuff. So,
and I guess, and going along with that as well, you've got guaranteed control of the rotary valve. Even with pneumatic valve springs that they use in Formula One, you get to a point where you can start to lose control of the valve contact on the cam lobe, and then ugly things happen very quickly.
And yes, so completely eliminated that. And as you said, that we're not visual here, but like you said, you've got some resource there, people can look things up. But the V10 latch was just beautiful, where the valves were just across the top of the cylinder head of the V10. They were all geared to driving each other. There was not even any intermediate gears. It's just a beautiful arrangement. And Andrew Thomas, my immediate boss at Bishop, designed this magnificent iris throttle.
Oh, okay.
So it's literally like a camera iris. It's just a complete, absolute masterpiece. So when it was completely open, there was nothing in the way of the air whatsoever, and took up hardly any space. It was just amazing.
With the advantage, obviously the barrel style throttle has the same advantage in that when it's open, it's seamless. There's complete flow. So there's the advantage there from that iris type, just the size and space that it takes up.
The size, the compactness, like a barrel throttle, you've got to have the barrel the size of the hole, basically, to accommodate the hole, which means it's quite big. Where the iris throttle was just basically, it was like 15 mil high plate that housed the mechanism. Like it was just, it was beautifully done.
Right. Now, one of the things, sort of just referencing that article that I mentioned, there's a significant advantage with the rotary valve design in that the sort of mass of the cylinder head, the size of the cylinder head and the height of the cylinder head dramatically reduced over a traditional poppet style engine, and therefore lower mass and a reduced centre of gravity height, which for a road car is probably mostly irrelevant, but for Formula One, people live and die by this stuff.
Yeah, that's exactly right. So that was a major advantage. Yeah.
At the point in that article, I think they were sort of claiming something like a 10% volumetric efficiency improvement over the traditional poppet valve F1 engines. And there was sort of talk as well in that article that they could hold peak volumetric efficiency up to something like 25,000 RPM, which is a nice number, but sort of begs the question, how relevant or useful is that when we still need to keep the pistons attached to the connecting rods, not to mention, of course, RPM limits.
Yeah, that's right.
Now, this kind of didn't unfortunately make it on track, did it? Can you give us a sort of understanding of where the wheels kind of fell off?
So when the V8 rules were announced, the V8 rules that were to come into force in 2006 were announced in 2004. And that basically said you just had to run poppet valve. So from that point onwards, the engine was not legal. So that sort of ended the whole program.
It seems to be a bit of a shame. F1, I guess, when I was growing up, I think was always a hotbed of innovation, and it was always sort of the talk about the trickle-down effect of this technology that's developed in F1, sort of making it to road cars over time. As I see it with the current F1 rules, they've almost set a rule book that really stifles innovation. That's how I see it. I don't know. Maybe I'm wrong. I wonder what your opinion on that is.
Oh no, I think that's very true. There's very little room for radical innovation there. There's certainly material science and that sort of stuff. There's scope for that sort of thing, but it's becoming more of like a spec class basically. Well, it's been like that for a long time, really.
Yeah. I guess the flip side of that coin is if you provide too much leeway with the rules, you can end up with a team that sort of just gets everything right and ends up so far ahead of the rest of the teams that it's not a fair fight. But I guess you could argue that happened with Mercedes in 2014 and then again with Red Bull from 2021. Obviously now it's sort of a bit more competitive, so I guess that still does happen, but maybe it'd be an order of magnitude higher. Regardless, from my perspective, I think it's maybe a bit of a missed opportunity that we're not seeing that level of freedom and innovation that maybe we're used to.
I think that's fair comment. Yes.
Where do we go to with rotary valve technology from here, though? I mean, it seems on face value there's definitely some pros, undoubtedly some cons compared to a pop-up valve. Are we likely in time to see this sort of filter into road car engines, or now with this sort of drive towards EV, is it kind of a dead in the water project, do you think?
Well, my old boss, Tony Wallace, he manages all the rotary valve stuff. He's pursued other opportunities along the way, but I'm not privy to that, to anything that might be happening there. So I guess the whole EV thing coming is or threat's probably a wrong word to use, and it's probably a bit exaggerated, but it is going to put a damper on a lot of internal combustion development and money and direction and that sort of stuff. So it's hard to say.
Yeah, I guess it'd be a big roll of the dice now for a major OE to start developing a significant change in direction with their engine technology for internal combustion when the writing's probably on the wall.
Yeah, I don't think anyone's going to get a budget to spend a heap of money on internal combustion engines.
Yeah, makes sense, but a bit of a shame. All right, we'll move on again. Lots of things to talk about in this interview and all quite unique and different, but your current business that you're running, GTpumps, a turbocharging company, again, quite a unique direction compared to what you'd previously been involved with. How did this come about?
Well, I guess I've just got a general interest in engineering. I just love engineering, and the turbocharger is just a particularly interesting device for what it does. And so, when I left the F1 stuff, I was sort of looking for something to do. We still had M&W thing chugging along in the background, and Wayne was sort of mostly doing that. And I just decided to get into doing turbochargers, and I chose let's do stock frame turbochargers. I had an Evo myself, Mitsubishi Evo 6 Tommy Mackinnon, and just sort of evolved from there. And I just like engineering, I suppose.
Okay. I guess The first question that comes to mind there is why focus on a stock frame turbocharger? And for those who aren't sort of picking up the pieces here, stock frame is literally just bolts onto the factory exhaust manifold, downpipe, oil feed, oil drains, etc. So dramatically simplified installation. But obviously it's then a very narrow focus product because it only fits that particular model of vehicle. A bit more flexibility in the Evo range because there's so many similarities between the different models. But compared to a universal fit turbocharger that you can put on anything, why did you go that stock frame route?
Well, I think it'd be just impossible to compete against Precision, Garrett, EFR, all those big guys. You wouldn't have a hope of competing with the resources I had. So I just went down the stock frame route. We just specialize in Mitsubishi Evolution and Subaru WRX and like directly related vehicles. And that's sort of like a little niche market that I parked myself in and just enjoyed doing that over the years. We've won Club Sprint at World Timer Track twice with our stock frame turbos. We won the Australian Tarmac Challenge. We've won Targa Tasmania. We've won the Evo Nationals. We've won the Subaru National. Actually, the Subaru Nationals held this year. We still came second outright with a turbo we built for a customer. So they obviously do the job. And just in my little humble market, I just try to do the best I can. And it's good.
There's still competitors in that stock frame market, and one of the obvious ones that jumps to mind is Forced Performance. They're probably one of the first to jump on that Evo stock frame turbo bandwagon.
Yes.
Fairly established big company over in the US. So how do you kind of separate yourself or get a point of difference from the other stock frame turbo manufacturers?
We're quite friendly with Force Performance. We've spoken to them a few times over the years, and I think Robert Young, this is probably jumping aside to a moment, but the UHF turbine that he's done for his turbos, I think that's probably the most significant thing I've seen in turbocharging since the whole thing started.
It does seem that those UHF turbine wheels have kind of almost got some magical combination of flow and response.
Yeah, that's right. So that, hats off to him doing that sort of stuff. But I think we had a bit of advantage in that the US exchange rate was so high that a lot of the FP stuff was quite expensive in Australia, and we still had a competitive product against his products. And so, we were able to exist in that market. And then I had, obviously, because we build them, we can repair them and everything in Australia. So that's a big plus for customers as well.
Yeah, it's a bit of a hassle when you've got to send something all the way back to the States at relatively significant expense and then be without it for a fair while. That kind of hurts.
Yes.
Yeah, just to be clear, I'm assuming here you're not actually manufacturing the core assembly of the turbocharger yourself. You're relying on OE production parts and sort of mixing and matching. Am I on the right track there?
That's right. But we do get custom compressor wheels all billet made. And we buy the parts in from various suppliers, but we actually assemble all the turbos in our Sydney factory. And that's an interesting story in itself there, that you would have heard like the VSR balancers, the vibration sorting rig, the big compressed air power things. Well, I couldn't afford one of those, so I built my own.
Of course you did.
As you do,
There's a theme that's run through this whole interview so far.
So, and I listened to your podcast with Robert and his turbo test stand and stuff like that. We actually did some similar testing in the University of New South Wales Aerodynamics Lab in Sydney, and we had a setup where we were using compressed air. So we were only measuring the performance of the compressor wheel, not the turbine wheel side, but enabled us to do some own compressor maps and that sort of stuff. So we have got into it, pretty deeply, and we just got our product range there, and.
Before we started recording, we were talking about these turbochargers and the fact that your journal bearing, with the exception, I think there was one you said you used a Garrett core, which is.
There's just a few in our range as a Garrett core. Yeah.
I think these days most enthusiasts sort of assume that journal bearing technology is sort of dead in the water. It's not really relevant these days. Ball bearing turbochargers are stronger, better, faster to spool, etc. What do you say to those comments?
I would say that I think in high boost applications, say over 30 psi, certainly ball bearing is a better arrangement. But in my stock frame, most of the customers are running in the mid 20 psi, and so that's absolutely fine for our journal bearing stuff.
To be clear, the limitation there, at least as I understand it, is not necessarily the journal bearings or the axial bearing strength. It's more the case of when you start running very high boost levels, the thrust bearing is the part that sort of takes a hammering, whereas the ball bearings sort of support the turbocharger in thrust as well and is much stronger in thrust.
Yeah, that's right. So that's the major advantage of the ball bearing turbos. But if you're not running over 30 pounds boost, it doesn't matter basically. So
what's the limitation, I guess, when you've pigeonholed yourself into using a stock frame turbocharger in terms of how far you're able to go beyond what the factory turbocharger was able to support?
Well, this is something remarkable with the Mitsubishi Evolution is because the turbo system was developed for Group A rally. So that's why in Group A, we got all these magnificent homologation specials with all these trick parts on the cars because they had to be, like you look at a Mitsubishi Evolution, they've got the full anti-lag system as on the factory car. And all the tables in the ECU are set to 0. So it doesn't do anything. So they made all these thousands of Evos, but they had to do that to be able to use that in the Group A rally and Group N rally. So this is the lengths that the factories went when they wanted to win. So the turbo system, I think on the Mitsubishi Evolution, I'm talking like Evolution 5 onwards, I think is probably the best factory turbo system that's ever been built on any car. Like we were able to fit like a bigger exhaust wheel into the factory turbine housing, and we can run, up to like over 400 kilowatts at the wheels on E85.
It's actually pretty impressive for a stock frame turbo.
You can run like 300 kilowatts on the wheels on E85, like with the stock intercooler. You know what I mean? Like there's just so much already there to play with, So that's why you can get this miraculous performance just with the stock frame turbo.
On that basis, I mean, these days we're always seeing articles about 4-cylinder, 2-litre turbocharged engines, street cars that are making 800, 900, 1,000 horsepower. And I think there's an expectation with people that are young and up and coming and getting into the car scene that, if you don't have 800 to 1,000 horsepower, then there's no point taking your car out of the garage. As I've sort of grown and driven more cars and figured out what I like and what I don't like, I would say that outside of the drag strip, probably a well-built 500 horsepower Mitsubishi Evo would decimate a 900 to 1,000 horsepower Evo on the street, particularly assuming we're talking about some tight, windy turns. So I guessing back to sort of like less is more, and my guess here is that stock frame turbocharger, if you're getting those sort of numbers you just quoted, that's probably more than enough for 85% of people in that market.
Yeah, absolutely right.
And then on top of that, the advantage you've got is that you've got a much more cost-effective installation because you don't have to custom fabricate an exhaust manifold, an external wastegate. Everything just bolts on.
Everything just bolts on. And we have the same thing with our Subaru range. Everything just bolts on. Yes.
Yeah. I guess given the way manufacturers are changing direction, I mean, Subaru is probably a bit different to Mitsubishi, who have completely cut their Evolution range. I'd sort of see a bit of danger in that you've got potentially a shrinking market. Is that something that's sort of on your radar, or are you looking at producing stock frame turbos for different brands, different models?
Well, no, I've always sort of specialised in those two brands, and yeah, the Evo market is shrinking. But for instance, we just released our new turbo for the FA24 WRX only a couple of months ago, so that's a car coming along that we're catering for. But yeah, I think it's a general reflection of that whole market, that whole four-wheel drive turbo market. There's less and less cars. I mean,
we're seeing less and less exciting models coming out, I think, from the showroom floor these days, with the notable exception maybe of Toyota with the GR Corolla and GR Yaris. There's just not a lot else out there that I find exciting.
There's not a lot else. And then, I mean, you've got the Euro stuff, which that might be cost effective to play with in Germany, but in Australia, the cost of those cars are so expensive. And I mean, there obviously is a market there for that sort of thing, but for your general club car people and stuff that always played with all the JDM stuff, yes, it's sort of just things are disappearing.
Yeah. I mean, from my perspective, I kind of see a bit of a a potential for some of the European cars. And example I'd give there would be like the Volkswagen Golf. There's obviously a wide range of those. We bought a Mark V GTI Golf just for some course development, and just with a tune alone, that picked up quite a significant amount of power, and it's it's not the fastest thing I've ever driven for sure, but it's a good little car. And I kind of see for the money you can buy these for, I think that Mark V Golf we picked up for about 9,000 New Zealand dollars. What's that, about maybe 5,000 US dollars? So it's quite a lot of car for the money, and maybe that's the way that the younger enthusiast market might be shifting towards, because it's about all that's affordable.
Yeah, it may well be that it may move more towards the Euro stuff. I guess that will play out.
Bit of a shame. But that's the world we're currently living in. Getting back on track, though, just I wonder if you could give us a quick understanding of the development path that you go through with bringing a new turbo to market, and let's use that FA24 as an example, seeing you've just released that.
Okay, so basically it's I mean, this is probably a sarcastic way to say it, but you have a look at how bad the factory turbo is, and that will give you some idea of the scope of improvement. So, most of the modern cars typically run a smaller turbocharger for good torque download, that sort of stuff, emissions and what have you. Yeah, so you just have a look at the sizing of all the housings, of wheel sizes and stuff, and see what wheels you can fit in there. What extra flow could we pick up with the different castings and that sort of stuff. So it's just a matter of having a look. And then, in the past, you might have a wheel combo that, works really well in an Evo or Subaru, and you think, oh, well, we'll go with that. And just, it's just a matter of doing some iterations there and stuff.
I guess if you've got something that you've already developed and you kind of know you've got a combination that works, that might be a little bit easier. But if you're sort of starting with something that maybe is a little bit newer and unknown to you, how many iterations of changes would you sort of typically go through before you're happy with the result? I mean, it's obviously a balancing act between high RPM power potential, boost response or boost threshold, and I think the OEs have really, really sort of heavily favoured that instantaneous punch when you touch the throttle, but of course you've then got a turbocharger that's just all choked up once you get higher in the rev range. So yeah, how do you sort of balance that?
Well, I think you've got to look at the peak power the customer might want, then also the peak power that the engine can produce, and that's your sort of limitations. And then that comes back to, okay, we're just talking about airflow. Well, then let's have a look at, the engine itself. Okay, so how much fuel do we have available? So it's all encompassing, really. You've just got to look at the FA24 has direct injection with a mechanical fuel pump. So obviously got limitations there. What will it flow? You've got limitation with indirect injection injectors.
So there's not really a lot of point putting a turbo on there that can massively outflow the potential of the fuel system, because you're just never going to be able to harness the potential the turbo's got.
That's right. You're going to lose all this boost response down low, and then you can't use the airflow at the top end. So it just makes no sense to sort of go in that direction. So it's a matter of just looking at all the parameters and just coming up with a workable position. Sometimes, for instance, with Evos, we have three different size turbochargers for the Evo range. So
yeah, that was going to be my next question. I assume it's not a one size fits all solution.
Yeah, that's right. So, but with the FA24, we actually just went with our medium solution. Now, all our wheel technology is quite mature. We've tested to death. We know what it does and that. So it's just a matter of choosing the combos there, and we know what that wheel combo is going to do. And with the FA24, we chose our sort of mid-range combo. And as the FA24 is actually 2.4 litre, it's high compression, direct injection engine, has a lot of exhaust energy, whatever. So with that engine, you want to just get rid of that exhaust. That's the main thing you want to focus on. Yeah.
Yeah. Okay. In terms of the other parts around the turbocharger, we sort of talked a little about the core and the wheels. In terms of the compressor and turbine housings, are you casting these yourself in Australia, or are you using production housings?
I buy them in from other suppliers, yeah. There's only so much you can do there, because all the tooling and everything just costs an absolute fortune. So, it's interesting. Like, we're using the same size turbine housing for our three different Evo turbochargers that go from 300 to 400 kilowatts, and it's still the same casting with a different machined out for a different wheel. So it's actually surprising. if the factory design is a well-designed thing from the start, it's surprising what range of airflows you can encompass and actually get a fairly good result.
Yeah, interesting. All right, Mark, I think we'll probably move towards wrapping this thing up. And as always, we've got the same 3 questions we ask all of our guests at the end. And the first of those is, what's next in the future for you?
Well, I guess I'm heading towards retirement, so that's a bit of a boring conclusion for me. But
well earned, I would argue, though.
Yeah, well, I hope so. I hope we've made a big contribution, I think, to the aftermarket industry. And when you think about all the things that happened since we started Haltech, it's quite remarkable when you look at the whole industry. Yeah,
no, really interesting, sort of what you've been through and how everything's changed. Next question, is there any advice you could give to a younger version of yourself, or perhaps one of our listeners, to help fast track where you've got to in your career?
I would say follow your dreams. I mean, that would be my advice to the young engineers: follow your dreams, because you never know where you end up.
I think that's good advice. I mean, I think as well, I've mentioned this numerous times in previous podcast episodes, but I think if you're doing something that you're passionate about, you're sort of the old saying, you'll never work a day in your life. I don't know if it's quite accurate. No matter what you're doing, there'll be tough times, and it's not always sort of rainbows and unicorns, but it's certainly going to be easier than doing a job you hate, which unfortunately I'd imagine probably half of the population around the world are stuck doing.
Yeah, well, I mean, I'm a farm boy from Australia, ended up in Formula One, so
how good.
You never know what can happen.
Absolutely. These days, I'm interested in your take, coming back to the start of this conversation, we talked about the diploma versus a degree. And these days, I think it's become easier to learn or pick up new skills, maybe without necessarily a formal qualification. I'm interested in your take on formal education versus learning through other means. What do you think?
I think if the information's good, it doesn't matter where it's coming from. I mean, when we did that compressor wheel development, University of New South Wales, I had 2 engineers do their undergraduate thesis, mechanical engineering students did the undergraduate thesis with me on the compressor wheel. So if you've got good knowledge in a specific area, it doesn't matter whether you've got a degree or not.
Yeah. Obviously, notwithstanding, there are vocations where you're not getting a job if you don't have a specific degree. But
yeah, like I've got 3 sons and they'll be all going to university. So one is already at university. Another one probably will start next year. So yeah, education.
Yeah. All right, our last question for today, Mark. If people want to follow you and see what you're up to, how are they best to do so? So website, social media?
Yeah, social media, GTpumps Facebook page. That's probably the easiest way for most people to find us. Or we can go to our website, whatever.
Okay, and we'll put links to those in the show notes as well to make it real easy for people to find. Look, Mark, it's been a real pleasure getting to hear your backstory. Very unique and diverse life experience, and it's been great learning all about it. So thank you very much for your time today.
Okay, thank you. It's been great.
If you enjoyed this episode of Tuned In with Mark Boxsell, we'd love it if you could drop a review on your chosen podcasting platform. These reviews really help us to grow our audience, and that in turn helps us to continue to get more high-quality guests. To say thanks, each week we'll be picking a random reviewer and sending them out an HPA t-shirt free of charge anywhere in the world. This is also a great place to ask any questions you might have too, and I'll do my best to answer them if your review gets picked. So this week, a big shout out to Bill1125 from the US, who has said, always learning something new, great listen. I love putting on the show and just getting to know great stories while learning something new about the automotive engineering sector. Well, it's great to hear that you are enjoying the podcast, Bill, and if you get in touch with your t-shirt size and shipping details, we'll get a fresh tee shipped straight out to you. All right, that concludes our interview, and before we sign off, I just wanted to mention, for anyone who's been perhaps hiding under a rock and hasn't heard of High Performance Academy before, we are an online training school and we specialize in teaching a range of performance automotive topics, everything from engine tuning and engine building through to wiring, car suspension and wheel alignment, data analysis and race driver education. Now remember, you've got that coupon code You can use podcast75 at the checkout to get $75 off the purchase of your first course. You'll find our full course list at hpacademy.com/courses. Important to mention that when you purchase a course from us, that course is yours for life as well. It never expires. You can rewatch the course as many times as you like, whenever you like. The purchase of a course will also give you 3 months of access to our gold membership. That gives you access to our private members only forum, which is the perfect place to get answers to your specific questions. You'll also get access to our regular weekly members webinars, which is where we touch on a particular topic in the performance automotive realm. We dive into that topic for about an hour. If you can watch live, you can ask questions and get answers in real time. If the time zones don't work for you, that's fine too. You're going to get access as a gold member to our previous webinar archive. We've got close to 300 hours of existing content in that archive. It is an absolute goldmine. So remember that coupon code podcast75. Check out our course list at hpacademy.com/courses.